Hi guys. So this is part 2 of the section 8-1 notes. In the previous video we looked at how to find a geometric mean and we reviewed how to simplify a radical expression. We'll be using both those skills as we're looking at some of the theorems and their corollaries in section 8-1. So let's jump right in and take a look at theorem 8-1. It says that if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. And so if I have this diagram over here where I have triangle QSR and angle Q has a measure of 90, if I draw the altitude that goes down to the hypotenuse, which would go from Q down to the hypotenuse and form a right angle. That's what an altitude does. Remember, it goes from a vertex to the opposite side and forms a right angle. So in other words, if I have this right triangle and segment QT is perpendicular to segment SR, so if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles that I've just formed, triangle QTS and triangle QTR, they are both similar to the original triangle, triangle QSR, and they're similar to each other. So that means I have three pairs of similar triangles that I just formed. So let's write out these three similarity statements. So triangle, let's look at this little one right here. Triangle, let's call it triangle QTS. Now that is similar to the original triangle, but I probably am not going to be calling it triangle QSR anymore because I have to be careful about the order that I put these letters in. So I said QTS. Now I know they're similar because they have angle-angle similarity. There's going to be a right angle right here, and angle S would be congruent to itself. Angle S is an angle of both the big original triangle and this new little triangle that was formed when I dropped this altitude down. So I need to make sure that I write my letters so that the angles that are congruent are in the corresponding order. So I started with angle Q up here, which is not one of the angles that I know are congruent. So that's going to match up with angle R of my original triangle. So I started with Q here. I'm going to start with R right there. Now my second letter was T, which is my right angle, so that's going to be angle Q of my original big triangle, and angle S is congruent to itself, so the S's should be in the same place. So I have triangle QTS similar to triangle RQS. Now next I would also have this triangle over here similar to the original triangle, and that's again because of angle-angle similarity, with the right angle here being congruent to the right angle of my original triangle and angle R congruent to itself. So let's call this one triangle RTQ. It is going to be similar to triangle RQS. Lastly, I have that those two triangles are going to be similar to each other. So that's going to be triangle QTS, which will be similar to triangle, now let's see, T was the right angle of both, and angle Q up here of triangle QTS is the angle that's going to be congruent to angle R, so I know I should have an R right there, and that would leave Q to be in this location right there. So triangle QTS is similar to triangle RTQ. Now what that means is, of course, because they're similar, we know that the corresponding angles will be congruent, and also we know that the corresponding sides will all be proportional. And that idea of the corresponding sides being proportional is what leads to the next two things we're going to learn, which is corollary 1 and corollary 2. So corollary 1 to theorem 8-1 says that when the altitude is drawn to the hypotenuse of a right triangle, then the length of the altitude is the geometric mean between the segments of the hypotenuse. So let's see what that means. we notice that when the altitude comes down, we drop this segment down that forms a right angle with the hypotenuse. It breaks that hypotenuse into two pieces. In this case, it's kind of like a short piece and then a longer piece. According to this corollary, in my right triangle, when I drop the hypotenuse down, in other words, when QT ends up being perpendicular to SR, then the altitude is the geometric mean between the segments. So in other words, we know that from the last video that the geometric mean between two numbers is the number that I can put both here and here when I put the numbers in the other two spots of my proportion. And since the corollary says that the altitude is the geometric mean, for this picture that means that the QT is going to go in both of these spots. And it's the geometric mean between the segments of the hypotenuse, so ST and RT. So I'll put ST in one of these spots and RT in the other. So with this altitude dropping down from the right angle to the hypotenuse, I know that this proportion results. And it really comes from this idea that there are similar triangles that get formed when you drop that altitude down from the right angle to the hypotenuse. This is just one of the proportions that ends up coming from all of this stuff from Theorem 8-1. So that's corollary 1, that the altitude will be the geometric mean between the segments of the hypotenuse. There's a second corollary to Theorem 8-1, and it says that when the altitude is drawn from to the hypotenuse of a right triangle, each leg is the geometric mean between the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. Now this one is a little bit trickier than corollary 1. You got to think a little bit more, I think, about what proportions result because of corollary 2, but let's work our way through it. So in this picture here, if the measure of angle Q is 90 and QT is perpendicular to SR, that's just a way of saying that QT is the altitude drawn from the right angle to the hypotenuse of a right triangle. Then we have two proportions that will result. Each one is dealing with this idea that a leg will be the geometric mean between the hypotenuse and the segment of the hypotenuse that's adjacent to the leg. So let's start with leg QS. We know that the legs are the sides of a right triangle that are not the hypotenuse. So QS is one leg and QR is the other. Let's deal with QS first. Now it says that the leg is the geometric mean. So I know that that means that QS will go in these two spots. And it's the geometric mean between the hypotenuse and the segment of the hypotenuse adjacent to or next to that leg. So I know the hypotenuse length, so SR, goes in one of these two spots, and this other one will be the part of the hypotenuse that's next to our leg that we're looking at, QS. So here's QS, that means ST is adjacent to or next to the leg QS. So ST goes in our other spot right there. Now that's for leg QS. There's also another leg, QR. It will also be the geometric mean between the hypotenuse and the part of the hypotenuse that's next to that leg. So QR can go in these two spots. It's the geometric mean. And the hypotenuse goes up here, and the part of the hypotenuse that's next to leg QR, RT, that goes right there. So these two proportions also result when we drop down this altitude from the 90-degree angle to the hypotenuse of the opposites, or the hypotenuse of the triangle. So we know that we have similar triangles. We know that we have these three proportions that all result because of those similar triangles. Let's see how we're going to put that into play in an example problem. So here you can see we have a right triangle with this altitude that's drawn from the 90-degree angle over to the opposite side. And so we have to, given a few pieces of information, let's find all these other lengths. So we'll start with labeling this picture according to what the given information is in part A. JR, it says, has a length of 16, and EJ has a length of 9. And we are supposed to find HJ, we'll put an X there, RE, well RE we actually know right away because RE is the length of the hypotenuse, And we should be able to add the 9 and the 16 together to get RE. So let's put a 25. We know that RE is 25. We'll put that right there. We need to find RH. Let's call that a Y. And we need to find HZ. I'm sorry, HE. So we'll call that Z. Now, before we jump in and try and find these values, let's write out the three ratios, or sorry, the three proportions that we know would be true because of corollary 1 and corollary 2 that we just talked about. And so that would be that, first of all, this altitude is the geometric mean between the portions of, or the segments of the hypotenuse. So that means that HJ would be the geometric mean between EJ and JR. It also, in corollary 2, tells me that this leg, EH, will be the geometric mean between segment EJ and the entire hypotenuse, which is segment RE. Also, from corollary 2, we know that HR, or RH, the other leg, it will be the geometric mean between this part of the hypotenuse, JR, and the entire hypotenuse, RE. So we know that these three proportions are all true in this diagram. Now, what I would do is I would come through and I'd say, okay, which parts of these proportions do I know? If I know that JE is 9, that JR is 16, and of course we figured out that RE is 25. So let's circle the parts in these that we know. In this first proportion, we know the length of EJ, and we know the length of JR. And so since these two spots are both going to be HJ, or what we've called X in our picture, we should be able to set up this proportion to find X. Let's keep going though. Let's look at in these other two proportions, what do we know? In the second one we know we know EJ, we don't know EH, but we know RE. And in the third proportion, we know JR. We don't know RH to start, but we do know RE. So you can see what we have here in these three proportions is really, even though there's 4 spots in each proportion, there's really only 3 numbers because these 2 spots will always be the same because we're looking at a geometric mean situation. So in each of these proportions, there's 3 potential numbers that can go in the proportion, and we know 2 of them in each one. So that means that we should be able to solve for the third number in each of these proportions. So let's go ahead and work on that. Let's start with finding the HJ here, filling in the numbers that we know in these 2 spots and finding HJ. So we know that EJ is 9, and we're going to find HJ, which we labeled as X in our diagram. So that's going to go there in those 2 spots, and JR is 16. So we're going to cross multiply, and that's going to give us that X squared is equal to 9 times 16, which is 144. And if X squared equals 144, then X equals the square root of 144. And 144 happens to be a perfect square, and it is 12. So X is 12, so HJ is 12. I'll put a 12 right there so we know we found that one. Next up, let's use this proportion to find EH. So EJ is 9. I can put a 9 on top. EH we called Z, so we'll put a Z there, and we'll put a Z there. And RE was the entire hypotenuse, and we said that that was 25. So we cross multiply that, we get Z squared equals 9 times 25, which is 225. So if Z squared equals 225, then Z would be the square root of 225. And you want to check that on your calculator. Whenever you're trying to simplify a square root, the first thing you always do is just check maybe you got lucky, maybe that this is a perfect square. So you type in square root 225 in your calculator, and what do you find? Oh, look at that. The square root of 225 is 15. No simplifying necessary. It comes out as an integer. Good deal. So EH, which was Z, has a length of 15. So we'll put a 15 right up there. And lastly, we can use this third proportion to find the length of RH, which we called Y. So we'll set up a proportion that has JR on top, so 16 over RH, which is Y, equals RH, which is Y again, over RE, which is 25. So we cross multiply and we get y squared equals 16 times 25, which is 400. So we know that y is the square root of 400. We type that in our calculator to see if we got lucky, and what do you know? We did. The square root of 400 is an integer. It is 20. So the length of RH is 20. So HJ was 12, RE was 25, RH was 20, and HE was 15. So just from these two pieces of information in this diagram, we were able to use corollary 1 and corollary 2 to find x, z, y, and of course the length of the entire hypotenuse. Now let's look at part B here. Let me get rid of all these measures that we tacked onto this diagram here. And let's look at what we're given and what we're trying to find for letter B. And so we know that JR in this one is 4, and JH right here is 2. And we have to find EJ, we have to find RE, which we know once we find X, maybe we can just add the 4 to the X and get RE. We need to find RH, which we'll call Y, and we need to find HE, which we'll call Z. So now, which parts of these proportions do we know? Well, let's circle the parts that we know. In this first proportion, we know HJ, which is in 2 spots, and we know JR. So there's just this one number here that we don't know. So we should be able to find EJ from this proportion. If we move down to the next one, what do we have? We have, let's see, we don't know EJ right now, we don't know EH right now, and we don't know RE right now. So there's actually nothing in this proportion that we know to start off with. Maybe that'll change, but right now we don't know any of that. In this third proportion, we know that JR is 4, we don't know RH, and we don't know RE yet. So right now we only know one part of the 3 numbers that are in this last proportion. So it looks like we need to start up here with this proportion. So let's work on that. Let's set up that first proportion. Let me go back to the pink color. I think it shows up a little bit better. So EJ is going to be X. So we're going to have X over HJ, which is 2. And that goes in both of these spots. And this spot right here is for JR, which is 4. So we cross multiply this one. We have 4 times X equals 2 times 2, and 2 times 2 is going to be 4. So 4x equals 4. We divide both of those sides by 4, and we get that x equals 1. So EJ has a value of 1. Put that right there. Now that also tells us RE, because we can just add the 4 and the 1 together. So RE has a length of 5. And that means that we have now this number, and we also have this number right here. So we should now be able to find EH using the second proportion. So let's take a look at that. EJ, which we now know is 1, over EH, which we're calling Z in our diagram. So those go there. And RE on the bottom here, which we now know is 5. So cross multiplying this gives us Z squared equals 5 times 1, which is 5, which means that Z is the square root of 5. Now 5 is not a perfect square, and it's a prime number, so it doesn't have any factors. We can't really do a prime factorization of 5 to try and break this down and simplify it. So that means we're done. Z is the square root of 5, so Z was EH, so we got that as the square root of 5. Now lastly, we're going to try and find RH. RH was Y, pardon me, and we can use this third proportion to find that. So let's set that one up. JR, or 4, over RH, which is Y, equals RH, which is Y, over RE, which we now know is 5. Cross multiply, we get Y squared equals 4 times 5, which is 20. So Y equals the square root of 20. Now 20 can be simplified because 20 is 2 times 10, and 10 is 2 times 5. So the square root of 20 is the square root of 2 times 2 times 5. And so we can see a pair of 2's right here, which will come outside the square root as a single 2, and the 5 is left underneath. So 2 root 5 is our value of Y, so RH is 2 root 5. So there you have it. That is the second part of section 8-1. We learned a couple interesting things that happen when we draw the altitude from the right angle to the hypotenuse of a right triangle. There's some similarities that happen between the triangles that you create, and because of that, there's some interesting proportions that you can set up involving geometric means. So good luck on any kind of homework that you're going to be doing over this stuff, and I hope to see you back for the next video.